Welcome to virtual algebra class. We are continuing our discussion of all the geometry on the GED test. And some people say, why'd you call it algebra class if we're doing geometry? Most of the geometry that's on the GED test is algebra-based, meaning we use formulas mostly to solve it. And so that'll be great. And we're going to look at and learn a new formula today. In order to do so, we need to understand some stuff about right triangles. So you think Pythagorean theorem, you should be thinking of right triangles. So let's go ahead and look at a right triangle. So what does it mean if a triangle is right? Well, it means one of its angles is a right angle. Now, mathematicians mark a right angle using this little square box in the corner. Have you ladies ever seen that little box before?
Yes.
Yeah, we use that box to signal that we're talking about a right angle. And a right angle is one that measures a perfect 90 degrees. And you know, 90-degree angles are what you hope your house has, right? Because if your house doesn't have 90-degree angles, it's all slanted over, it's going to fall down. If you don't have 90-degree angles in your house, you're calling the carpenter, you're really teed off. Okay, ladies? Same thing, you know, like 90-degree angles are why I can't build the bookshelves from IKEA, because I go to build, mine don't have 90-degree angles, and so my husband has to do it. You know what I'm talking about, ladies? Okay, so those are the kind of angles we're talking about. So let's define a right triangle as a triangle with one 90-degree angle. It's only ever going to be able to have one, also known as a right angle. Okay, that being said, if a triangle is right, there is some language that I can use about this triangle, okay? We have special names for the sides. Okay, so first of all, the two sides that hug the right angle. Notice that they make an L shape around this right angle. And that's helpful to us because their name starts with an L. Those are known as the legs. Notice I don't label them leg one and leg two, or first leg and second leg, or they're just legs in general. They could be different measurements, but they are just interchangeable as legs. Okay, so a right triangle has two legs around that right angle, and then it has that third side. Notice the third side is across from the right angle. Some students think of it as the slanted side, but we call that the hypotenuse. And the only reason I know how to spell this is because I Googled it in my last class. You guys are getting the advantage of Kate already looked at this. So hypotenuse is a tricky little word to spell, but there it is. It's that side across from the right angle. A couple things we should realize about the hypotenuse. One, I think just looking at it visually, besides the fact that it's across from the right angle, we can tell that the hypotenuse is actually the longest side of this type of a triangle. On a right triangle, the hypotenuse is always the longest side. Turns out that little fact is going to help us in a lot of cases. So this is something that you just have to know. However, I think if you sketch out a right triangle, it's pretty easy. It's not like you have to work hard to memorize this one, because I mean, just visually looking at this right triangle, I think it's kind of obvious that the hypotenuse is the longest side. And you could certainly bust out a ruler and measure if you didn't believe me. That being said, now that we know this information, I have a really good news for you. Every right triangle in the entire world, regardless of its measurements. So little right triangles, big right triangles that have one really small side and one really long side, you know, right triangles that are rotated in space, but they're still right. Every right triangle, regardless of size, shape, or rotation, has a relationship between its three sides. The three sides, as it turns out, of a right triangle are related. Now, it's interesting because that relationship is not easy to see at first. I don't have a ruler, so what I'm going to do is I'm going to create my own unit. We could name this unit after me. This is the Kate right there. Isn't that a beautiful unit? There's my unit. So I didn't have a ruler, so I don't know inches, I don't know millimeters, but there you go. There's my unit. Now we're calling it the Kate. And I'm going to introduce you to one right triangle that's really easy to see this relationship. It's known as the 3, 4, 5 triangle. So what I'm going to do is I'm going to make a right triangle. It is 3 Kates across. So I told you I'd call that the Kate. We're calling that the Kate. Here we go. We're going to go 1, 2, 3 Kates. We're calling that a Kate. Now I'm going to come up from here and go 1, 2, 3, 4 units that way. Are you cool with that? And now if I come across, it should take 5 to connect. 1, 2, 3, 4, 5. Now I wanted to start with this. Do you see that it's about 3 of my units across, 4 of my units up with a hypotenuse of about 5 units? Can you ladies see that?
Yes.
Now I'm going to do something weird with these numbers. I'm going to draw squares. I'm going to draw squares. So I know, and we were working on that when we were working on the concept of area, that if I have a square with a side length of 3, it is not only 3 across, or 3, up and down, it's also 3 units across. You might be thinking, why is Kate drawing squares on triangles? I promise I'll show you. But if it's 3 units here, then I end up with 9 square units. Okay, let's do the same thing with our 4 over here. This side, I'm going to draw a square over here as well. So once again, if I have 4 units going across here, I'll draw my 4 on the inside. Then on a square, squares have equal side lengths. So I'll also have 4 going up and down. Now I have a question for you. When I look at the squares on both of those legs, I have 9 squares on the one leg. I have 16 squares on the other legs. How many total squares do I have? What's the sum of those squares there? 16 squares and 9 squares gives me?
25.
25. I agree with you. I'll end up with a total of what we call 25 square units, or 25 squares. Okay, now I want to relate that to the hypotenuse. Take a look when I draw a square off of the hypotenuse. So it's going to be a little cockeyed because the hypotenuse is at an angle. But if I go 5 across this way and I go 5 up and down that way, I end up with a 5 by 5 square. We know it's a square if it has the same measurements both ways. How many little squares are in that square?
25.
25. Okay, so what you just proved to me was that if I square the 2 legs and add them together, I'll get the same number as if I squared the hypotenuse. Let's write that out mathematically. If I square the 2 legs, can we call the 2 legs A and B? Are you cool with that? So like if I square the first leg and I square the second leg and I add those answers together, it will equal the square of the hypotenuse. Let's call the hypotenuse C. You cool with that?
Yeah.
This is a very, very famous formula. I bet you've even heard it. I start saying it to students, A squared plus B squared, and they can usually finish even if they have no idea what they're talking about. They don't even know how to use it, but they're like, equals C squared. They just shout it out into the distance. They know this formula. It has a name, this relationship between the squares, and it is known as the Pythagorean Theorem. If you ask me how are the 3 sides of a right triangle related, I would tell you they are related by the Pythagorean theorem. The sum of the squares of the legs is equal to the square of the hypotenuse. Now I'm too lazy to spell the sum of the square of the legs, so I wrote it in math speech. Square, square, sum. The sum of the square of the legs is equal to the square of the hypotenuse. The really cool thing is we can use this formula to solve all kinds of problems. I highly suggest that if you have a GED formula sheet, you pull it out right now, because as it turns out, the Pythagorean theorem is on your sheet and you can mark that up. Okay, so right next to the Pythagorean theorem, you're going to see it in the bottom third of the sheet. It's like the 4th formula up from the top, I think. It says A squared plus B squared equals C squared, but it doesn't give you any notes about it. So unless you know what the Pythagorean theorem is used for, you won't know when to use it. So write this down. What is this used for? Now, it could be used for 2 reasons, actually. First reason it could be used is to prove a triangle is right. If it's right, this relationship will be true. We're going to see a couple problems like that today. But most commonly, what most of the time you'll see it used for is to figure out the missing side of a right triangle. So to find a missing side of a right triangle. Now look at this formula. How many variables does it have in it? How many letters?
3.
It has 3, an A, a B, and a C. We know that algebra only works for us to find a missing quantity if we only have 1 letter left. So in order to use this formula to find one missing side, you would have to know the other 2 sides. Okay, so if you knew A and B, you could use it to find C. If you know B and C, you could use it to find A, and so on and so forth. You'd have to know 2 missing sides, and then you could use it to find the 3rd. So draw yourself a little triangle on your formula sheet. Now, it really doesn't matter which way it's oriented. I happen to be constantly drawing it this way because this is the way we often draw it, but this thing could be turned anywhere in space. But make sure you know that your A and your B are your legs. So A and B are the legs. Because if you plug into this formula wrong, you get the relationship wrong, it won't work for you. It'll just give you a bunch of nonsense. And C is always that right across from the right angle hypotenuse. Okay, so A and B are the legs and C is the hypotenuse of this right triangle. As long as we understand that relationship, we're going to be able to use it for all kinds of things. I am going to pull up some example problems. So number 1 says, is the triangle below a right triangle? So remember the first thing I said we could use the Pythagorean theorem for. We can use that Pythagorean theorem, that relationship between the 3 sides of a right triangle, to try to prove that a triangle is right. Currently, I don't know. I don't know if this is right. There's no marking here. There's no proof. I mean, it looks like a right triangle, but that's never enough proof in a geometry class. And so what I can do here is I can prove that it's right by busting out the Pythagorean theorem. So the Pythagorean theorem says that if I square the 2 legs and sum those squares together, the sum of the squares of the legs, it should be equal to the square of the hypotenuse. Okay? So what I'm going to do is I don't know if these 2 things are equal right now. I don't know if the left-hand side is equal to the right-hand side because I don't know if it's a right triangle. This is only true when it's a right triangle. So what I'm going to do is I'm going to plug it in and I'm going to test it. If the left-hand side really is equal to the right-hand side, then this really is a right triangle. And so I'm careful. I don't know about equality. Okay, so I'm not solving here. What I'm doing instead is I'm plugging in the numbers, A, B, and C, and seeing if the 2 sides end up equal. So the trick here will be to guess which one is C. It's super important that you have your C right or the Pythagorean theorem will fail you. So remember that the C, the hypotenuse, was always the longest side. So looking at this guy, which number should I plug in for C?
13.
13. I will square 13 on the right-hand side here. Now on the left-hand side, I will get the sum of the squares. So I will, of the legs. So I will square the first leg and then I'll add it together with the square of the second leg. And you might say to me, well, which one's A and which one's B? And I'll say a leg's a leg, is a leg, is a leg, is a leg. I don't care. A, B, whatever, a leg's a leg, okay? And that's what I meant by they're interchangeable. Not that they're the same length, but they're both legs. Doesn't matter which one you call A or B. Now let's just simplify the left, simplify the right, see what happens. Do they... Sorry, that was too funny. I said, anybody mad at me? Bianca said, not yet. It's coming, honey. It's coming. Okay. So I'm going to do the simplification on the left and the right, see if they match up. So let's work on the left-hand side first. So we know by the order of operations that we should handle any exponents before we do addition. So I squared 5 and I squared 12. And you see why we reviewed this concept last class. Now order of operations says I add and subtract last. And so I get 169 when I simplify the left-hand side. Now let's check out what would have happened on the right-hand side. 13 squared or 13 times 13. Again, I did ask you to memorize this one. If you don't have it memorized, you could certainly do that in your TI by typing 13 and then the X squared button. And when I do, I get 169. Do you notice I got the same thing on the left-hand side that I got on the right-hand side? They are equal. So what I've just proved here is that this must be a right triangle because only right triangles have this relationship between the sides. And so is the triangle below a right triangle? Well, yes, indeed, it sure is. Is anybody mad at me? Does that make sense?
A little bit. So are you looking for just one right angle or are you looking for all?
I wasn't finding an angle this time. All I was doing was proving. It was a yes or no question when I said, is the triangle below a right triangle? So notice when I plugged in, I didn't have any letters left. Can you see that, Bianca? My A, my B, and my C all went away?
Yes.
Yes, which tells me that I wasn't trying to find A or B or C, not find a missing measurement. Rather, I was trying to see if this relationship was true. And because the left-hand side came out equal to the right-hand side, I found out that the Pythagorean theorem was true. If the Pythagorean theorem is true, the triangle is a right triangle. Does that make sense?
Yes.
Okay, cool. We will see it. We're going to look at our next few problems, like spoiler alert. We'll use it to find missing things, but this isn't just not that particular type of problem.
So so what you're saying is that if the numbers are equal on both the left and the right-hand side, then it is a right triangle?
Yes, because I got something. It made it true. An equal sign is a fact. Like this left-hand side is equal to right-hand side. So if I can prove, if the left-hand side really does come out equal to the right-hand side, I've discovered something true. If the 2 sides did not come out equal, then it was a lie to begin with. This was never a right triangle.
Okay.
So let's look at one more example like that, see if that helps. Number 2 says, is a triangle with side lengths of 6, 7, and 10 feet a right triangle? So once again, I know that I have these measurements of 6, 7, and 10, but I'm not guaranteed that this is a right triangle. Maybe, might not be, no way of telling unless I see if they satisfy the Pythagorean theorem. So I'm going to start with that relationship, a squared plus b squared equals c squared.
So the 10 is the hypotenuse?
The 10 would have to, if this is a right triangle, the 10 would have to be the hypotenuse because the 10 is always the longest side.
Okay.
Okay, now the A and the B are both legs, or would both be legs, so they'd be interchangeable. Now again, I don't really know if these two sides are equal. I don't know. That's what I'm trying to figure out if I'm trying to see if this is a right triangle. And so I will do the math on either side and see if they come out equal. I'm not solving for a mystery letter here. Instead, I'm trying to see if my equation is true. 6 squared is 36. 7 squared is 49. I need to do any exponents before addition, and 36 plus 49 would give me what, 85, I think? Now on this side, on the right-hand side, I'm looking only at the right-hand side, I see 10 squared. If I were to square 10, I would get 100. So did I get a relationship of equality? Is 85 equal to 100?
No.
No, 85 is not equal to 100. It's not, and I just used this is the math symbol for not equal to. I don't think you have to have that memorized for the GED, but that's what I'm talking about. 85 is not equal to 100. This triangle did not satisfy the Pythagorean theorem, the relationship between the three sides of a right triangle. So therefore, this triangle cannot be right. Is the triangle with these side lengths right? No, it is not. So people actually use this, or can use this, in various industries when they know they have to make perfect corners. They can measure the sides and see if the measurements they got satisfy this relationship. If it didn't, they don't have a perfect corner. It's especially useful for really big things or really, when it might be challenging to see if you have perfect angles going on.
Well, I could have really used this last weekend when I was hanging drywall.
Yes, absolutely. Yes, there are so many applications in construction. I had one of my guys in my class who used to be a general contractor. He's in my class because, he hurt himself. He can't work in contracting anymore. He needs a new job. But he was just going, oh, through this whole lesson, figuring out why so many of the things they do in the field work, it's because of this formula. He never knew the formula, but he knew dozens of applications of it, so very interesting. This is more typical of what students expect to do with the Pythagorean theorem. So the first thing I told you we could do was we could prove that a triangle is right. But that's not the only thing we can do. Anytime we have a formula, if we know that formula will work for us, then we can use it to find a missing variable. Okay, so number 3 says find the missing side of the triangle below. Now, I would argue that I know this is a right triangle. How do I know this is a right triangle, ladies?
Because of the square in the bottom corner.
Exactly. Somebody told me. So somebody was kind enough to label it. Look at that. They put that little right angle in there. That's what proves to me mathematically that this is a right triangle, because it has that right angle of 90 degrees. Therefore, if they just tell me it's a right triangle, well, dear goodness, I can assume that the Pythagorean theorem will be the relationship between the three sides.
Will they do that in the test? Will they put that box there if it's really not a 90-degree angle?
No, never. It's never used as a trick. Okay. Mathematicians are very straightforward. If we use that symbol, we mean that symbol.
Okay.
Yeah. Oh, good question. Love it, love it, love it. We're not super creative, by the way, mathematicians. We're going to use that symbol the same way every time.
Okay.
Okay, so I have a squared plus b squared equals c squared. This is the relationship between the three sides. I know I can use it because I know this triangle's right, and so I know I have equality. That being said, that means I can use it to find any missing letter. So we just have to, just like we've always done with formulas, substitute into it, and then we'll be able to find out the missing variable. But the key here is substitution. So really important for me, I want you guys to draw a little arrow going away from your right angle, because as long as you can find the hypotenuse, you can't go wrong with the Pythagorean theorem. It doesn't matter if you mix up the legs, it's the hypotenuse that matters. So get across from that right angle and realize that this thing that I don't know that I'm looking for is the C. This is the hypotenuse. Knowing that the other ones are interchangeable as A and B, I'm going to plug in. I'll plug in 48 for my A. I'll plug in 36 for my B. And obviously, just like I said, not obviously, but just like I said, I could have done it the other way around. The legs are interchangeable. It won't make a difference. And now, just like always in algebra, I can start doing any simplifying and solving when I have these algebraic equations. I see some simplifying I can do, some forwards math that I know how to do. And remember, your TI can do simplifying for you even if it can't solve things. Okay, so I can square 48 by pressing 48 and the x squared button. And I do get 2304. Now I haven't added yet, so I'll keep that addition symbol. And I can get square 36, and I get 1296. And that whole left-hand side is equal to c squared. I can't square c because I don't know what c is, so I'm just going to leave it there for a while. Just let it chill. Can you see the next thing that I can do? There's more simplifying on the left-hand side that can be done. Those are just two numbers. I know how to add. I'm going to go ahead and do that math. I'm going to add 2,304 with 1,296. And I get 3,600. Okay, now on the right-hand side, once again, I don't know what c squared is. I can't simplify it. I just drop it, equals c squared. And now's when the real algebra kicks in. We were just doing arithmetic up to this point. We were working on one side of the equation. But now I'm in trouble. No more simplifying left to do. It's time to work to get c alone. Does anybody remember how to isolate c? We got to do the opposite, and I would argue with you guys that the opposite of squaring is not fractioning or dividing. What's the opposite of squaring?
Square root.
Square root. Bingo. The thing students forget most often is probably one of the most frequent things to come up in our geometry formulas. So don't forget that the opposite of square root, I'm going to pick up a different color so you can see. I'm going to take the square root of both the left and right hand sides. Can somebody explain why I took the square root of both sides? Why did I do that? Before I was only working on one side.
I don't know. I remember a long time ago you said whatever you do to one side, you have to do to the other.
If you make a change. So Bianca, the math didn't tell me to square root. It said to square. I was just disobedient. I said, no, I'm not squaring because I don't know how to square C. I'm going to do the opposite of what you told me. I'm going to take the square root. So when you make a change, you do it to both sides to keep it balanced. Does that make sense?
Yes.
Yes.
Okay, so square and square root cancel on the right-hand side, just like I wanted, so that C will be alone. And on the left-hand side, there's the math to do. Now, if you were with us last class, you might know the square root of 3,600. I do. You might know that you can just square root the 36, 6, and take half the zeros. 60. If you don't know that, that's okay. You would have a TI for the test. So to get square root, I would have to press second because it's in green, and then that x squared button, and then I would put in 3,600 and press enter, and it would give me 60. Is anybody mad at me? Does that make sense?
But you still have a letter left. Is that okay? Because it's isolated?
Yes, exactly. That's how you know you're done in algebra, when the letter's alone. As soon as the letter's isolated, I know. So what I'm saying here is that I know what C is. C is not a mystery anymore. An equal sign means the same as is. So C is 60. Algebra's weird to get used to. It is. But once you do, it makes so many things so much easier. It's that ability to work backwards and forwards in the same problem. So I have 60 equal to C. Now this is the final answer now, so I should know 60 what? So ladies, any ideas? 60 what?
I thought that both sides had to be the same number for this to work, right?
When both numbers are the same, you are proving that the triangle's right. So you have all the numbers, but you don't know if it's a right triangle. Right. So those were the last two problems we did. They just asked us, is it a right triangle? And we said, I don't know. Let me plug in the numbers and see if the two sides end up equal. Does that make sense?
Yes.
Yes.
Now, in this case, we didn't need to prove it was right. They proved it was right for us. By using this right angle, they said, this is a right triangle. And so because it's a right triangle, I can now use this relationship to find any missing side.
Okay.
So 2 different ways to use the same formula.
Okay.
Does that make sense?
Yes.
But you can only use this to find a missing side if you know for sure the triangle's right.
Okay.
Cool. Okay, so I did find out that the C is equal to 60 inches. So now I just used my Pythagorean theorem differently. I used it to find a missing side, and the missing side length here is a 60 inch. This guy's 60 inches long. And that's how most of the problems will be that you'll use this with, Bianca. Most of the problems that you'll see, they'll tell you it's a right triangle, or there will be some kind of proof within the problem that it's a right triangle, so you can use this formula to find a missing side. This number 3 is the more common problem type you're going to see. So let's look at a bunch of more examples. Okay, so number 4 says find the length to the nearest tenth of the hypotenuse of a right triangle. Again, we see our proof. This time they did it in words instead of symbols, but they did prove to us that we have a right triangle by just saying it. And then it does tell us that there's legs of 8 and 11 centimeters. So we know that the legs are on either side of that right angle, hugging that right angle. So I will label these as 8 and 11. Are you cool with that?
Yes. Yeah.
Now, this is the thing I don't know. This is the thing they told me to find. They told me to find the length of the hypotenuse. So this is the unknown. Now, let's think about this. We know that if it's a right triangle, the 3 sides are related by this formula, a squared plus b squared equals c squared. But I told you it's super important to identify which one was c, which one was the hypotenuse. So you tell me, of these 3 sides I'm looking at, which one's the hypotenuse?
The one with the question mark.
Exactly, the one we don't know, right across from that right angle, that's the C. So once again, I'm going to plug in, and again, A and B are totally interchangeable, but C's a mystery. I can't plug in a number because I don't know what it is. And now we simplify before solving. It's not always necessary, but it is always usually a wise step to simplify before solving. So 8 squared is 64, 11 squared is 121, and that sum is equal to the square of the hypotenuse, whatever that is. I don't know. So I write c squared. Okay, on that left-hand side, I can continue simplifying. So 121 plus 64 is 185. And you guys should definitely watch my calculations because we're going to help me not make idiot mistakes on YouTube. And 185 is equal to c squared. So now all my simplifying is done. There's no work left that I know how to do on the left-hand side. There's no work that I know how to do on the right-hand side. It is time to start solving, working to get the letter alone. How would I solve something like this?
Square root.
Exactly. The opposite of square is square root. I'm making this change, so I do it to both sides in order to keep my balance. On the right-hand side, squaring and square root cancel so that my C is alone just like I wanted. And on the left-hand side, you're going to need a calculator. If you had anything like this on the GED, any Pythagorean theorem application problem, I would expect you to have a calculator. But I wanted to do this problem for a reason. Most of your calculators will be in the wrong mode. You will go to put in your answer, and I just would love to show this to you because students get so stumped by this. And because they tell me their calculators are broken. So they press second, square root, just like you're supposed to. They type in 185, just like you're supposed to. And then they get so mad at me. I hope you can see this because their calculator tells them that the square root of 185 is 180 square root of 185. And they tell me, Kate, my calculator is broken. It's not doing math. And I say, it's not broken. You forgot something I told you. Anybody remember if your calculator doesn't give you the kind of numbers you're expecting, what's going wrong?
The mode is incorrect.
Thank you. I am in what's known as math print mode. And as you guys know, because I talk about it all the time, math print mode acts like a mathematician. It will not give you an ugly decimal. Remember that the square roots of ugly numbers are what we call irrational decimal forms that go on and on forever. If you're in math print mode, like a mathematician, they will not want to give you an ugly decimal mode. You're going to need to switch to classic mode. So hit the mode button, arrow down over the word classic, press enter to select it, clear out of that screen, and now when you type the square root of 185, you will get a decimal answer. Can you ladies see this time it did spit out a decimal answer for me? Exact same problem, different form of an answer. 13.601, and there's a lot more decimals after that, 4705, but I am not even trying to write down all those decimal places. So I'll just write down a few in order that you guys can see my rounding. And now As usual, when I have long, ugly, disgusting decimal answers that go on and on, there are some rounding directions in my problem. It says find the length to the nearest tenth. You guys remember how many decimal places was the tenths place?
1.
Absolutely. So after 1 decimal place, I will put my chopping block down. I will consider not that number, but the number I'm about to throw away, the next number. That 0 is not big enough to matter because it's not 5 or higher. And so I will decide that that's about 13.6 centimeters long for that hypotenuse. So number 5 says an isosceles right triangle has legs of 13 meters. Find the hypotenuse of the triangle. Round your answer to the nearest hundredth. So there's a lot of language going on here that they're going to assume you know. But first of all, we have been told it's a right triangle. So let's go ahead and draw ourselves a right triangle. Now, they tell us something about this right triangle. They tell us that it's an isosceles. That's just a straight up vocab word that you either know or don't. Do you guys know what it means when a triangle is an isosceles? It means it has 2 equal sides. An equilateral triangle has all 3 equal sides. Equilateral, that one's probably easier to remember. But an isosceles has 2 equal sides. So I said this was an isosceles right triangle, and notice that plural there. I said it has legs. 13 meters. So because it's isosceles there, both of those legs are 13. And again, they said to find the hypotenuse of the triangle. So very similar to the last problem, just that little extra vocab word thrown in. Since I know it's a right triangle, I can feel free to use my Pythagorean theorem to solve for any missing dimensions. My 13s are my 2 legs, so they will get plugged in as A and B. And my hypotenuse is what I'm looking for. And so my C here is an unknown. Now, looking at this problem, if I were to square 13, you guys know I would get 169, and 169 equal to C squared. And now I got to add those together. And I'm feeling slow today, so you should check me in your calculator. But what do we get? 338? I have self-doubt issues. 338, beautiful. And that's equal to C squared. Now almost done. As you know, the opposite of square is square root. So let me pick up a different color so you can see it. I am going to square root both sides. Why? Because square rooting is a change I decided to make in order to isolate my variable. So I do it to both sides to keep my balance. Square and square root cancel so that my C is alone. And I know you guys get sick of me saying things the exact same way, but I sure hope that you hear my voice in your head when you're doing your test, because it's better than panicking and forgetting how to do all the math you ever knew. And the square root of 338, if I'm in classic mode, will be the decimal 18.384, yada, yada, yada. Now, a final step here when you get one of these nasty, ugly decimals, see if you should round. So I do see just very direct, straightforward rounding language. Round your answer to the nearest hundredth. So hundredth is how many decimal places?
2.
2. So I'll cut it after 2 decimal places this time. Again, I won't consider the hundredths place. I'll consider the next place and ask myself if I was big enough to matter. So 5 or higher will round up, but that's not 5 or higher. And so I wasn't halfway through my digits yet. So I'm closer to 18.38 than 18.39. Let's call that 18.38 and 18.38 what? Well, 18.38 meters. All the Pythagorean theorem ever finds is side lengths. Side length is always a linear measurement. It will be measured in plain old linear measurements. So number 6, very brief. A mathematician must have written this one. Find x. Have you guys seen that meme on the internet where the student just goes, here it is? There's a little thing that goes around where the student's like, there, I found it. Anyway, not what I mean. If I say find x, I mean the same as solve for x, right? So cute, funny, very nice, made for a great meme. But we're going to have to do some math here. Do you notice the proof in my problem that this is a right triangle? Can you see it? Right there, absolutely. Proof. I've proved it's a right triangle. Feel free to bust out the Pythagorean theorem. This must be true since this is a right triangle. And I can plug into it what I know, but hopefully what you notice this time, they've given me one of my legs.
But not the other.
Exactly. And this time they've given me my hypotenuse. Again, the most important thing here is that you can identify your hypotenuse. If you don't put the C in the right place, it'll all be for not. It'll be all a bunch of nonsense. So I'll put my C, my 39, the hypotenuse over here on the C side. Now I always have the slew of hands in the air, but Kate, is 15 an A or is 15 a B? And I'll say again, legs are legs are legs are legs. I don't care if you call 15A or you call 15B. I promise you, if you do good math, we're going to get the same answer, whether you call it A or you call it B. So I'm going to call it B because I find students make less mistakes when they plug in after the letter. I don't know why. Okay, so we always said after you substitute, you can do any simplifying there is to do, and then you can solve. Go back and forth across the equal sign. I see this time my problem's a little different. I see simplifying I can do on the left-hand side and simplifying I can do on the right-hand side. Do you guys see any simplifying on the left-hand side?
Yeah.
Yes.
Yeah. What can we do over there?
15 squared.
Exactly. We can square 15. So I won't touch my a squared. I won't touch my plus, but I will simplify 15 squared. And that's 225. And of course, you could, if you didn't have that memorized, you could type 15 square into your TI. Your TI will simplify for you. And I don't know 39 squared, so I'll do that. I'll type 39 in the x squared button in my TI, and I get 1521. Okay, now this problem is a little trickier than the last problem. Why? Because there's no more simplifying to do. If I look at the right-hand side, there's obviously no simplifying because it's just a single number. Okay, but looking at the left-hand side of this equation, here's the left.
Can we square root them both?
Good. We're going to, but not yet. Oh, good, Bianca. So there's two things over there with A this time. There's a square and there's a plus 225. Both of those things I can't put together with A because A is a mystery. And so all I can do is get rid of those things. So this is actually a two-step equation. I need to get rid of the 225 and I need to get rid of the square. And we said that when we were solving, that's what we're doing right now, getting rid of things, solving, we would work our order of operations backwards. So really important that we move away anything that's adding or subtracting first. And so before I square root, which I'm going to do, Bianca, don't worry, but before I square root, I am going to take away the 225. So let me bust out a different color so you guys can see my balance change. If I want to take away the addition of 225, I'm going to have to do the opposite. I'm going to have to subtract 225. Now, the rule of solving is literally I can do whatever I want. I can be as disobedient as I want to be as long as I do it to both sides. So I'm going to jump the equal sign to keep my balance. And I'm going to subtract 225 over there as well. Now, after making this balance change to both sides of my equation, let's see what's left. On the left-hand side, adding 225 and subtracting 225 will cancel. So all I have left is my a squared. And on the right-hand side, there's the math to do. We'll take 1521 and we'll subtract 225. And again, you can do that part in your calculator. The calculator can do those calculations for you even if it can't handle the algebra. And I get a squared is equal to 1296. Now it's time to get rid of that square. So the opposite of squaring is, as Bianca pointed out, square rooting. I will square root both the left and the right-hand side. On the left-hand side, square and square root cancel, leaving me with A. And on the right-hand side, there's the math to do. The square root of 1296 is 36. Now, this doesn't need to be rounded. I didn't get a disgusting decimal. It terminated all by itself. But I have 36 what? 36
millimeters?
Those are just plain old meters, but yeah, absolutely. I misread. No, it's okay. If I wanted millimeters, a lot of students don't know the abbreviations and I always kind of brush right by them. If I wanted millimeters, I'd need 2 M's. 36 meters. Sometimes when you plug into formulas, you'll end up with only one-step equations to solve, but sometimes they're more than one step. And if they are, that's when we'll rely on those algebra skills we learned in the past. If anybody needs a review on solving multi-step algebra, we do have in our very first unit, we have solving two-step equations and solving multi-step equations. Both of those videos are available in our online class, or if you're on YouTube, and you can get a review of why we do what we do in algebra, which will help you, again, on these geometry problems as well. 7 says solve for the missing dimension below, round your answer to the nearest tenth. Now, I realize that I titled this video, The Pythagorean Theorem. So you're pretty sure that the first step is always to write down the Pythagorean Theorem. But, you know, when you go to take the GED, it's not going to be Pythagorean Theorem day. So give me some proof in this problem that the Pythagorean Theorem is what I need.
There's a right triangle type of thing at the top.
Cool. It's a right triangle, and I'm missing one side, but I know the other two. That is when the Pythagorean theorem works for you. That's the only time, by the way. It's when you have a right triangle and you want to find a missing side. Okay? So beautiful. I shouldn't say that's the only side. I just thought of an exception as soon as I came out of my mouth, but not on the GED, okay? So sometimes two sides will be the same. There'll be two missing, but since they're the same or they're in relationship, we could deal with it. But anyway, not on the GED. So that being said, I am going to bust out the Pythagorean theorem. And again, the hardest part is knowing what to substitute where. I want you to take your pencil. I want you to start at the right angle and go right across from the right angle. Go across from the right angle. What's the side across from the right angle? Always, always, always C. I'll keep your A the way it was, but B then is an unknown. And for C, I will plug in 5.5. Are you cool with that?
Yes.
Now, again, A and B are interchangeable, so I wouldn't have cared if you'd have called B3. It doesn't matter, but the C mattered. Okay, so let's do our simplifying before we start solving. Do you see any simplifying I can do here?
On the left-hand side, the 3 squared.
Absolutely. We know 3 squared simplifies to be 9. Now, I can't add b squared to that because I don't know what the heck b is, but I sure can do the simplifying on the right-hand side, and I'm going to use my TI for that. I'm going to type in 5.5 and the x squared button, and I get 30.25. Do you see any more simplifying that I can do?
I don't think so.
Yeah, no, you're right. There's no more forwards math, so it's time to start solving. It's time to start the real algebra. So I've got a couple of things to get rid of if I want B to be alone. I hope you can see that.
Mm-hmm.
The 9 is over here hanging out with B. So is the little floating 2. Those are the two things I need to get rid of. Now, we said when we're solving, which is what we're doing now, we're working to get the letter alone. We're solving. We need to go in that opposite order of the order of operations. So I need to move anything adding or subtracting first. So I'm going to have to take that 9 away. Make sense?
Yes.
How could I make that 9 go away?
Subtract it?
Exactly. That's a positive 9, so I could subtract it away. Whoa. If I wanted to do this by hand, I should put my 9 right there. Not that it matters because I'm actually doing it in my calculator, but just for those of you who are going to do it by hand, you would put your 9 right there. Whole numbers in the ones place line up with whole numbers in the ones place. So on this left-hand side, taking 9 away from 9 does zero out, and I have what's left is positive or plus b squared, but that's positive b squared. Yeah, I don't need to brag when the numbers are positive. I'll drop that. So I get b squared is equal to 2125, and you can verify that for me in a TI if you don't believe me. Now we're almost done. B is almost alone, but I have to get rid of a square. So in order to get rid of a square, we do the opposite of squaring. Sorry, I'm just writing over in the other color.
Square root.
Exactly. I'll take the square root. Again, I'll do it to both sides because I got to keep my balance when I'm solving. Square and square root cancel, so B is alone. And I ran out of cool. I'm going to do the square root of 21.25 in my calculator. No wonder I didn't know it. It's gross. It's an irrational. Ugh, it goes on and on forever. I hope there's some rounding directions. Yeah, indeed. I see round my answer to the nearest 10th. You ladies told me the 10th was 1 decimal place. I'll cut it off after 1 decimal place. I'll look at the next number, see that it's not big enough to matter, and decide that is just 4.6 feet for that length. Pretty straightforward problems. These are not really, they had a lot of words to them, but these were not word problems yet, what we usually refer to as word problems, because they don't have real world applications yet. We were very just direct and straightforward. We told you exactly what to do. Does the Pythagorean theorem show up in word problems? Indeed it does. And we know how much the GED loves a word problem. It's their favorite. So we better not keep our understanding on such a simple level that a word problem makes us cry. Okay. Now, I actually kind of have life regrets about this page because I drew the pictures for you. I've seen ones on the GED where the picture's not there. Like these ones already have the picture. So I'll do these two, but then I'll show you an example of one that maybe might come up as well, okay? So number 8 says, a plane takes off from the airport and climbs steadily for a distance of 500 meters. At that point, the plane is 400 meters from where it took off. how high above the ground is the plane. So I didn't have to draw my picture because they drew it for me. How nice. But I can see that my plane took off from the airport, like they said, and climbed steadily. We see that taking off motion, climbing steadily for 500 meters. At that point, the plane is 400 meters from where it took off. So when you say how far is the plane traveled, yeah, it went for 500 meters, but we're measuring distance that it's traveling along the ground. You know, like if we want to figure out how close it is to Florida, we're measuring along the ground, not like at an angle into the sky. And so at that point, it's 400 meters from where it took off. And then we're asked how high above the ground is the plane. Now, this is an interesting one because they gave you the right angle, but I still say even if they hadn't given you the right angle, I would know that this is a right triangle. And the way is because of the language. Mm-hmm. How high above the ground is the plane? Whenever you measure height of something, you go straight up from the ground. You know, if you're measuring my height, I don't lean over, okay? We're going to go straight up from the ground to measure my height. Okay, so whether it was a tree or a plane or whatever, it would be important to have your measuring rod straight up and down from the ground at a perfect right angle in order to measure height. Does that make sense to you?
Yes.
So it was the fact that they said how high that proved to me that it had a right angle, even if they hadn't had the picture. But they do. So you don't have to think too much, I suppose. But I can bust out the Pythagorean Theorem. There it is, a right triangle. The Pythagorean Theorem will work. Now, again, the hardest part is finding C. So don't plug until you know where C is. So which one's C?
The 500 meters.
The 500 meters. Absolutely. I will plug 500 in for C. Again, it does not matter whether you call the 400 A or B. I'll call it B because students tend to struggle less. And I have done my substitution step. Once you've substituted, just like always in math, if there's any simplifying you know how to do, by all means, go ahead and do it. I see some simplifying. I know what 400 times 400 is because I learned that lovely trick with my round numbers last class. It would be a 16 with 4 zeros after it. Even if you didn't know that, you're welcome to your TI. You would have it on this problem. Same thing with 500. I know what it is. It's a 25 with 4 zeros on its butt. Again, if you struggle with that, feel free to bust out your calculator. Now, I can't simplify anymore. I can't square A because I don't know what A is. I can't add jack to A squared because I don't know what A squared is. It's time to start solving. What should I get rid of first?
What's next to the A, right?
You should go in opposite order of operations. So you should get rid of anything adding or subtracting first. So do you see which one of these numbers is adding or subtracting?
The 16,
exactly.
Or no, the 160.
So I'll get rid of the 1600 from both sides, or not 1600, sorry, 160,000. Ooh, I bet you I get some comments on that. Anyway, I'll get rid of the 160,000 first. On this side, adding 160,000 and subtracting 160,000 will cancel, leaving me with just an A squared. And on this side, let's see, I'll get 9, 1, 2, 3, 4. Now, one more thing I have to do to get this thing alone, I got to get rid of the square. So the opposite of square is square root. I made that change, so I'll do it to both sides to keep my balance. And let's see what my new equation is. Square and square root cancel, leaving me with A. And this I can do mentally in my head because I'm so lazy. I'll get a 3 and half the zeros. But even if I couldn't, you could do it in a calculator. I'm literally just too lazy to pick up the calculator and push that many buttons. Okay, that's how you know a real mathematician. Okay, so I get A is equal to 300. 300 what? 300 meters. Is anybody mad at me?
Mm-mm.
Then we'll just look at this last word problem, and then like I told you, I'll write a couple so that you can get practice sketching things out, because it would be very like the GED to not give you a sketch. I bet Serenity can amen you. Or amen me on that one. They have word problems where they don't sketch it out for you and you're not quite sure what shape is going on until you draw a picture.
Okay.
So, but number 9 says, Jack is flying a kite with a string 42 meters long. His friend Pedro is standing directly underneath the kite, 27 meters from Jack. I just watched Napoleon Dynamite, so I'm super into Pedro right now. Okay, how high is the kite above Jack's head? So once again, we see there's Jack with his string 42 meters long. There's Pedro. If I were to measure how far apart they were, I would measure it on the ground, 27 meters. But if I want to know how far above Pedro's head the kite is, I would go straight up. straight up. So that's definitely a right triangle. Since I know that this is a right triangle relationship right here, I can bust out the Pythagorean theorem. And again, as long as I know what C is, the Pythagorean theorem will never do me wrong. So which side is C?
Going to be where the 42 is.
Absolutely. Right across, directly across from the right angle is that 42. That's what I plug in for C. A and B don't matter. Again, they're interchangeable. I'll call 27B. A squared plus, I don't have 27 squared memorized. I'll do it in my calculator. I get 729 equals 42 squared is 1764. I have simplified. Time to start solving, working to get the letter alone. So I see the opposite of adding 729 is subtracting 729. I'll do it from both sides. Let's see what our new equation is after we made that balance change. Adding 729 and subtracting 729 cancel, so the only thing that'll be left on the left-hand side is a squared. And on that side, there's the math to do. And since I'm feeling slow, I'll do it in my calculator, and I get 1035. I'm almost done, but too many students stop here. Don't stop here. The letter's not alone. You're not done. Get rid of that square by taking the opposite, the square root of both sides. On this side, square and square root cancel, leaving me with a. And on that side, your calculator can handle gross. The square root of 1035 is 32 point yada, 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 yada. Lots of stuff. Now, if you notice on this particular problem, I have no rounding directions. It just says how high is the kite above Jack's head, no rounding directions at all. If this were on the GED, it would definitely be multiple choice. So you'd be able to look at your multiple choice answers. They might all be, rounded to the ones place. They might all be rounded to the tenths place, the hundreds place, but you wouldn't have two answers that could possibly work. Okay, so it's probably about 32 feet. It might be 32.2 feet. I would rely on my multiple choice to guide me in my rounding choices if this were on the GED. Since it's not, I'll put in the word about so you guys know I had a signal that I rounded as I chose. I don't know a single one of you that if I asked you to measure something anyway, you'd be like, oh, it's 32.17 feet. No, y'all would be, oh, it's about 32 feet. Okay, good enough for government work. Okay, so let's look at the ones where you might have to sketch it out on your own. I forgot to put these in there. I should have. It was short-sighted to me, but I'll just write a few, and I'm sure y'all will be able to hang. So it's like the never-ending class again, because you know how much I like to talk. Let's call this number 10 here, and let's get the very, very typical GED problem, the ladder. 15-foot ladder is leaning against a wall. The base of the ladder is 2.5 feet from the wall to the nearest tenth of a foot. How high up the wall does the ladder reach? Now I have to tell you, most students fall into one of two problem-solving categories when they look at a word problem like this. The first is the panic category. Y'all just panic, give up. It's too hard. I can't do this. And you cry a little maybe, and you say, I'll never pass my GED. Category one. Second category, the random musher of numbers. Y'all just pick up this calculator. You have no idea what you should do with these. You just press them and you hope and you pray. If I just push some numbers with some operations, maybe it'll all work out in the end. But anyway, whether you're just giving up or random mushing, neither one is a problem-solving strategy, okay, y'all? Can you just, draw me a picture? Could we start with, I'll just draw, even if I can't do anything else, I'll make a nice little picture for Kate's office wall. Okay, that's what I'd like to see. So here we go. We have a ladder leaning against a wall. Can you show me what a ladder leaning against a wall can? I bet you guys know that if I have, the ground and a wall, you don't have to be a beautiful artist to draw me a ground and a wall and a ladder leaning against my wall. Okay, I think that you guys can agree that this is no work of art.
No.
But I drew a ladder leaning against a wall, okay? And I can put some numbers on it because they told me some information. What can I label? What do I know here?
The base is 2.5 feet.
Yeah, so where would I put that 2.5?
On the bottom?
Yeah, right here. From the base of the ladder to the wall, that's 2.5 right there. Okay, I know another number. What else do I know?
The ladder's 15 feet.
The ladder. So where am I going to put the 15 then? It's not even a trick question.
By the ladder?
On the ladder? Sure.
Yeah.
Sounds like a plan. I'll label the ladder as 15 feet. Okay. Now, what am I looking for? What are they asking me to find?
How high up the wall does the ladder reach?
Yeah, how high up the wall? How tall am I actually going to be? How high up the wall does the ladder reach? Well, they're looking for that measurement there. From the ground to, that's the thing I don't know, from the grounds to the top, to the ladder there. Now, I hope that you guys can see that this is a triangle.
It is.
Can you see the triangle formed in here? I mean, spoiler alert, I know it's triangle day today, but it won't be triangle day on the GED, so you'll have to draw a picture to figure out what's going on. But look at that triangle. Is it a right triangle, though? There were no words in there that said right triangle. Can you guys think of is this a right triangle?
Yeah, I would believe so.
I would believe so too. I would believe so too. Or once again, I would get on the phone with the contractor and I would be one pissed off client of this contractor. If the wall is not at a right angle, my house is falling down. Okay. Yep. So just as a general rule, when you walk around, walls tend to be at right angles to the ground, or people, you know, especially in where we live, we're blessed and lucky that we have well-built houses for the most part in the United States. Walls are at right angles to floors. Okay, so good. I can assume that's a right triangle based on my knowledge of reality and the world around me. That means I can feel free to bust out the Pythagorean theorem. I'm sorry, I'm going a little slowly through why I get to use the Pythagorean, but once again, when you have this on the test, you won't know what to use. It's the problems will be all mixed up. So you'll have to reason your way through it. Okay, and again, if I want to use the Pythagorean theorem, I better know which one is C. So which one is C?
The 15 feet.
The 15, right across from that right angle of the floor and the wall is my C, 15 squared. Again, it's interchangeable, which one you call A and which one you call B. I'll plug 2.5 in for B because I find students make less errors. That's really the only reason. I will simplify. I'm going fast through this because I think you guys got this concept, except it helps if you actually type the right buttons in your calculator. So 2.5 squared is 6.25. Oh, I knew that. Why did I need a calculator for that? And 15 squared is 225. I will subtract away the 6.25 because I am solving now. And I'll get A squared is equal to, I'm feeling slow today. I'm definitely doing this in my calculator. Oh, I knew that. It's easy to say that you knew it after you see it in the calculator. So I get A squared is equal to 218.75. And now, of course, in order to get rid of a square, I must take the square root of both sides. Square and square root cancel, leaving me with A. Not A squared, just A, Kate. And there's the math to do. And if you're super lazy like I am, let me teach you a TI trick. If you don't want to type in that whole big ugly number again, you can take the square root of your last answer. A way to do that is to press second, and then that little square root button, which as you guys know is above the x squared. And then hit second again, because right above the minus sign in green, there is answer, ANS. So if I put the square root of the answer, I don't even have to type in that long ugly number, and it tells me it's about 14.7901, yada, 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 yada. Okay, you cool with that? Do you notice any rounding directions?
No. Nearest tenth.
Nearest tenth. So I'll take it to one decimal place, and hallelujah, finally I had something that I was throwing away that was worth a darn. 9 is 5 or higher. It's more than halfway through our digit system, so that means that I was really closer to 14.8 than I was to 14.7. We'll call that about 14.8 feet. So my ladder's not reaching all the way up the wall, but, you know, at least 14.8 feet up the wall. Okay. How's that? Is that okay? I think 10 problems is a lot of problems, isn't it? We feel good with this? Yeah.
Yes.
Like, please stop now. So thanks for coming. I love not talking to myself. And I'll see you next week.